This one, yesterday I explained about the shell element local axis. Normally shell elements, if you do not rotate the local axis, the default is this one is 1, this one is 2. So because of the bending moment due to lateral load, this two direction concrete will crack. So we have to reduce the F22 component to 0.75. If you reduce the moment component M11, M22 of the shell element, it will not affect anything. For the flat slab, we have to reduce to 50%. In that one flat slab, we have to reduce M11, M22, M12. For the shear rigidity, we do not reduce in the girders and the columns, but we have to reduce in the shear wall. For the shear wall, we reduce the in-plane shear rigidity to 50%. For the axial rigidity, we do not reduce in any members. These stiffness modifiers are different from ACI chapter 10 stiffness modifiers. In ACI, for the girders, we reduce 0.35, for the shear wall 0.7, slightly different from ACI. And for the flat slab, in ACI it reduced 0.25. Here we reduce 0.5. And for the link beams, for the conventional reinforced link beam, we design as a girder, normal moment resisting frame girder, and we reduce that moment rigidity to 0.5. For the diagonal reinforced link beam, we reduce to the stiffness, moment stiffness modifier to 0.2 because it is highly cracked. If you want to calculate that diagonal reinforced link beam, the moment stiffness modifier, you can get the formula from in New Zealand code. When we use detailed formula, it is varying between 0.15 to 0.2. That's stiffness modifier. But in this example, I use 0.2. And then we have to reduce the stiffness modifier of the diaphragms. In this example, there is no podium level, podium and basement. This is the simple example. But in the real building, we have the diaphragms. We have diaphragms in the podiums and basement levels, which we have to take care about the shear transfer. This is the tower, and then we will have the 1 or 2 level diaphragms in. This is the ground level, and it will continue to the basement levels. And there will be a swirl spring here. So the seismic force coming from the tower will be transferred to the podium diaphragms as well as the ground level diaphragms and the basement levels. Especially here at the ground level, the seismic force will transfer from the tower to the soil. So in this load path, there will be a lot of in-plane stresses in the slab of the basement, ground floor level and basement levels. Not only that, in this sudden change, also there will be significant force transfer from the tower to the podium level frames. So we have to take care about those diaphragm design. So for the flexural rigidity of the diaphragm, we reduce to 0.5. That one is the in-plane moment. For example, this is in plan, this is the diaphragm plan, and then your tower is located in the middle of the diaphragm. So the load coming from the tower, and this is the retaining wall. This is the swell spring. So this diaphragm will act as a one beam with a point load in the middle. So there will be a lot of tension stresses in this zone, and the compression stress will be in this zone. So we have to check this flexural behavior of the diaphragm. So we have to check this F11. Not only this one will be F11 stresses, but if the load is coming in this direction, this one will be F22 stress. So we reduce the F11 and F22 of diaphragm to 0.5. This one, shear rigidity, it should be, sorry, this one is not correct. It should be F12. There, not only the flexural stresses, it will generate the shear stresses in this direction like a beam. Normally, when we do the performance-based design, for the code-based design, we use ETABS because this is linear analysis. And then use the same model for from ETABS. We just modify the stiffness modifier for service level evaluation for response spectrum analysis, and we check service level in ETABS as well. But for MCE level check, we normally use either SEP 2000 or Perform 3D. This one, we model the geometry of the, first we model the geometry of the building in SEP 2000, and then we start adding the nonlinearity in the members. Here I will show you some modifiers in the model. For the columns, we have to use the stiffness modifiers. Here 0.5, 0.5. And for the link beam, this one is the conventional reinforced link beam. We reduce moment stiffness modifier 0.5. And also we add the reinforcement in the steel. This reinforcement at the left-hand right end of the link beam. That reinforcement is coming from the preliminary design, which we design according to the code. And this one is the diagonal reinforced link beam. But for the diagonal reinforced link beam, we do not need to specify the reinforcement because we are going to add the shear hinge separately in that link beam. And these are the material properties that we have defined using the expected material strength. I will explain you this concrete material properties later. One important thing is when you define the material properties, we have to take care of these weight per unit volume. Sometimes we copy the steel material properties and change the modulus of elasticity. of the concrete, and then we forgot to change the weight of the material, so this can create this will increase the weight significantly. And for the expected material properties, when you define, not only multiply the concrete strength Fc prime with 1.3, you have to recalculate the modulus of elasticity of the concrete using that Fc prime. And I will show you the shell sections. For the slab, I use 0.25 for all moment stiffness modifier. Then I will continue the modeling of the shear, nonlinear modeling of the shear wall. In this model, I models the nonlinearity in shear wall and link beams only. The other members are elastic models. This is the shear wall reinforcement layout. In this building, I use this green zone. I use vertical reinforcement of 0.8% and confinement reinforcement of 15 legs, 12 millimeter diameter bars at 150 millimeter spacing. It means for example, this green leg, I have the vertical reinforcement of 0.8% and the confinement reinforcement of 15 legs. 15 legs means this is the confinement reinforcement. 15 legs means in this direction, x direction, I have 15 legs back. In the longer direction, I use only 2 legs. This is diameter 12 at 150. So these legs are have a spacing 150 millimeter. But in this so I do not provide any confinement. So only the vertical bars and the horizontal bar for the shear reinforcement. Not no legs here. So most of the boundary zone reinforcement are 0.8%, but middle reinforcement, which one that I use is only the minimum one, which is 0.25%. In the shear walls, for the highly seismic zone, special reinforced shear walls, the minimum requirement of the vertical reinforcement is 0.25%. Same thing for the horizontal reinforcement. That 0.25, we have to put 0.25% in horizontal reinforcement. Then I model the nonlinearity of the concrete material and the steel material for the shear wall. So we have two types of concrete. One is confined concrete, and another one is the unconfined concrete. In confined concrete, we have different types of confinement. In the previous slide, we have the 3 types of confined concrete with 15 bars. Another one is 6 bars, and third one is the 9 bars. So I will show you the defining of the materials for the confined and unconfined concrete. Here I define the concrete materials to be used in the shear wall. Type 1, 2, 3, 4. 4 is unconfined concrete. In confined concrete, first we have to go to advanced material property data and then go to nonlinear material property data. Here this one is already, the points are already reduced. I will define another concrete material. Define materials, and then first you have to go to stress strain plot and then show and modify metadata. Then you have to go to rectangular code. Then you have to define the confinement bar yield stress. Here is expected strength is 484 megapascal and the longitudinal spacing is 150. The diameter of the confinement bar is 12 millimeter diameter, and then we have to put the number of legs. For example, if we define for the number 1, we have 15 legs. 15 legs, and the one leg is, the length is about, sorry, I have to check the length. The length is about 2.5 meter. So 2.5 for the X direction tie legs, we have 15 legs, and then center to center distance between X direction parameter tie leg. So 2.5 meter, 2,500 minus, for example, cover and cover. Assume that 100 millimeters, so 2,400. And then for the Y direction legs, we have 2 legs only, and then the center to center is we have thickness of 700 millimeter. So if we assume that cover is 100, so it will be 600. Then we have to update the plot. Then click OK. After that, you have to convert to user defined. Otherwise, if you click OK and then continue, next time when you open that material property, that the reinforcement information that you put will be lost. So we have to convert it to user defined. So all the coordinates of the stress strain plots will be saved. This is the stress strain plot of this concrete material curve. But here you can see there are a lot of points in that stress strain plot. So when we analyze the nonlinear, when we analyze that model, if we have many points, the analysis time will be very long. So we have to simplify we have to reduce the number of points. So what we did was we copy all these coordinates coming from the material concrete material properties, and then we reduce the number of points in Excel file. I will show you the Excel file. this one for concrete one. This is the okay. The red one is the coordinates of the stress strain curve coming from the program directly. Then we reduce to few number of points. The blue one is the modified one. So after we have to adjust manually to get the same shape of this curve. But after we modified that one, the E value should be close enough. The original, the E value that we calculate from F prime C should be same as the when we check the slope. That slope should be close to that original E value. Because if we reduce too much number of points, the E value can be changed. So we have to maintain the E value. Here is about 13 points, and then I reduce it to 7 points. Then I check for and then I continue for other concrete types. This is for another concrete number 2, and this is for number 3, and this is for number 4. Number 4 is for unconfined concrete. Then I compare the stress strain plots with different levels of confinement. Here you can see the concrete number 4, which has no confinement, has very low ductility. For the other confinements, we have significant ductility and strength. The strength is also increased. So after we define the nonlinear materials for the shear walls, we have to define the shear nonlinear layer shell elements. This one is the import form that I showed you. This is the modified stress strain curve, and this is the comparison. And then I will go to nonlinear layer shell. This one, yesterday, as I already explained, we have the different layers, but for the practical purpose, we do not need to model the horizontal reinforcement layer in the shear wall. We will consider only the nonlinear flexural behavior. So we considered the vertical reinforcement layer, 2 layers, and concrete membrane behavior and concrete plate behavior. So the total number of layers is 4 layers. This one I have explained before. For the concrete layers, for the membrane layer, we have to use the full thickness for the concrete membrane, and we have to use this concrete 1 material properties. This one is important because if we use the linear material property, other material properties that we do not consider the confinement effect, the shear wall will not be ductile. So we have to use the material properties that we already modified with the confinement. So this shell is for the leg number 1, and then we consider the S22 as nonlinear. This is for vertical direction. And for the concrete plate behavior, we do not consider the nonlinearity in all components, but we still use the concrete 1 material. And then we have to define the vertical reinforcement properties. For the vertical reinforcement, we applied 0.8%. So we have to multiply 700 with 0.008 and then divided by 2, so we will get the equivalent thickness for the reinforcement. So those reinforcement, we are using the rebar material, but in rebar material, normally in the fault properties, the number of points of that material is not as much as too many as concrete. So if you want to reduce, it is still okay. So in this one, I think I do not reduce the number of points, but we have to rotate the material angle because this one is uniaxial material. So there is no S22 behavior component. So we have to rotate 90 degrees. Then in plane bending stiffness, we reduce to 25% of moment of inertia. So I have to define for all legs. Here I have I have 4 types of legs. So I have to define the shear properties for these 4 types of legs of the shear wall. Then I go back to the model and then area sections. So shear wall 700, 1, 2, 3, 4. These are the layer definitions that I have defined. This is for the shear wall leg number 2 with the concrete 2 and steel is same. After that, I have to assign in the model. Here you can see the different layers, different types of shear wall elements according to the confinement effect. So these orange ones are the unconfined concrete shear walls, and these are the concrete shear walls. Then I will continue the nonlinear modeling of coupling beams. We have 2 types of coupling beams. One is the diagonal reinforced, which has L by D ratio is less than 4. The length of that link beam is, here is 2 meter and the depth is 0.7 meter. So the ratio is 2.85, which is less than 4. So we provide the diagonal reinforcement. In the code, if we use the diagonal reinforcement for the beams which has L by D ratio less than 4, the ductility is quite good. So we use the diagonal reinforcement.